And it's a huge pleasure for us to welcome on stage Daniele Zonca. He holds a Master of Science from the University of Milan. He's now a model server architect at Red Hat. And more importantly, he's one of the organizers of Papers We Love, a great meetup in Milan. If you happen to be in that city, feel free to join. All the events are free. Of course, it's a community event. So Daniele, thank you very much for joining us. And he will be talking about serving GenAI models on Kubernetes. So 2 buzzwords, I'd say, in one title. It's not bad.
I also added the LLM in the subtitle.
Oh, man. So it's like 3 buzzwords in 7 words. It's not bad. If someone in the lightning talks want to challenge these, we are free to get challengers. So Daniele, again, thank you very much, and the stage is yours.
Thank you. So, thanks for having me. I'm going to be, I come from, let's say, an industry perspective, so we essentially developed software for enterprises. Red Hat built the software infrastructure in an open source way for a big enterprise or for a company that has, in any case, the scale in terms of size that requires the type of component, and also that has the challenge about running on-premise, so you cannot maybe share the model, you cannot share the data. So I work from Red Hat. I'm an architect for model serving, capability in OpenShift AI product. I'm writing a book about generative AI and Kubernetes. I found one open source project, and I'm part of different community upstream. So Red Hat, everything that we do in Red Hat is open source. We have upstream community. You can join, you can ask, you can contribute, you can use the software. So let's start, let's say, with a bit of introduction about, let's say, the challenging about why LLM scaling, so serving and scaling LLM inference is challenging. So, okay, transformer architecture. Attention is all you need. That type of diagram. I mean, I don't have the background, and I'm not going to go very deep on this, but we have essentially the encoder phase, the decoder phase. The reality is that the vast majority of models that we currently use are decoder only. So all the class of models, like from OpenAI, Meta, they are essentially in decoder only models. From an execution, from a serving perspective, there are essentially 2 phases during the generation of text. Well, the generation of the output in general. There is the pre-fill phase, that is where you take all the inputs, so all the prompt, you parse all the prompt, you process all the prompt, and you produce the first token. And then you have the autoregressive phase, so that everything, let's say, at every step, you take previous input, so all the input, the additional token, and you generate another token, and then you generate another token, and then you generate another token. So what makes hard to serve generative AI, and there is also a quote from OpenAI saying that they are still losing money even with the $200 per month subscription. So even with the subscription that is the most expensive, OpenAI is still losing money. And they know what they're doing. So I'm pretty sure that they already optimized pretty let's say, a lot of their infrastructure. Is that the main hardware component that you need to serve LLM is GPU. And there is this kind of 2 different phases, and we will see that pre-fill is compute-bound. So it uses a lot of computation, while the code phase is more memory bandwidth-bound. So it moves a lot of data. And that means that the type of impact on the infrastructure that you have, it's very different. In addition, the computation of the attention grows quadratically. So given that we are now using a lot of, so the input, even with RAG, it's very big, and the output that produced, it's even bigger, you can see that this is a pretty clear scalability issue. The outcome is that you take very expensive hardware. So when we take an H100 GPU from NVIDIA, that is one of the industry standard at the moment, it's like $200,000 or $300,000 per setup, not per single card, but per server. So it's an expensive hardware, and you still have a low throughput. So it's not ideal, of course. So let's look at, the execution of LLM takes different phases. So now I'm focusing about the computation of the attention part that use Q, K, and V. They are all metrics that are, let's say, multiplied essentially together. So in the pre-fill phase, you're parsing all the input. So you're processing all the input token at the same time. But every time you do another step, essentially you are producing a single token. So the K and the V gray box here are the same of the previous computation. So you would like to reuse them. You don't want to compute that twice. essentially you need to cache that. And essentially you are, so that at every phase, so every time you generate a new token, in reality you are reducing a lot the number of computation that you perform because you can cache a lot of the previous computation. So there are projects that has been created. So when you maybe try locally, maybe use Olama, or you use a similar project that you want to run if you want to run your model that are based on usually a project called the Llama CVP. When you look at about production use case, usually you really are looking at component that can scale a lot, that can use everything that you give them in terms of resources. vLLM, it's an open source project. Red Hat is one of the main contributors. We acquired the company, Neural Magic, on purpose just to get a better knowledge of that project that is designed to scale LLM serving in production. So you can use it as a library, as a Python library, or you can use it as a REST API. It accepts its input based on the model, of course, that you're running, text, images, video, but only produce text. So it's not covering diffusion type of architecture. It supports, I would say, every model, open source that you can find, or the vast majority. It's a very active project. There are like hundreds of PR every month. So it's a very, very active community. And it's a multi-accelerator. So you can use not just NVIDIA, but you can use AMD, you can use Google TPU, you can use essentially every type of accelerator that you can find in the market. The market is still like 90+% still NVIDIA, but there are like many other options, especially, for example, if you're using Google Cloud or if you're using AWS, they build their own accelerator for their system. And you can exploit that, and usually they cost less in terms of cost per token. So vLLM originally introduced a very old idea, essentially memory management, paged memory. So the KV cache, it's a block of memory that is pretty big. It grows with the size of the generation, and originally it was a single big block. And every time you were allocating all of them. So it's inefficient. So this is a problem that we already solved in, let's say, computer science for operational system. We introduced the concept of memory pagination. So you split you split the single block in different pages, and then you introduce a lookup table that gives you the possibility to resolve, given the page ID, essentially, to where the block is. That it seems to be like a reasonably simple optimization, and it is, but it opened the door to many other optimization, because at that point, maybe having the possibility to reuse the whole cache for another request is very unlikely to happen. But if you have two different prompts that has the same prefix, like the system prompt that is always the same, the previous block from the previous computation is still the same. So you can reuse and don't compute again across two different requests. So let's now look at the infrastructure requirement if you want to run that, let's say, by yourself. You need the GPUs, for sure. I mean, you can run on CPU, but it's more like you can generate like 1 token per second. I mean, it's more like for toy problem. If you're talking about like large language model with like, I don't know, 70 billion of parameter or even bigger, or a mixer of expert type of architecture. Of course, you also still need the CPU and memory, quite a lot. You need the storage, because each of those models can easily be 10 gigabyte, 100 gigabyte. The biggest model, like Llama 405, it's not 1 terabyte, but it's close to 1 terabyte of disk. And then, of course, a network, because you are moving a lot of data across the network. And guess what? Kubernetes can already manage essentially all of these. So Kubernetes is the de facto standard infrastructure software that you use to serve LLM. Even OpenAI is using, at least they mention it, and in a case that they are scaling an infrastructure like to more than 7,000 nodes of Kubernetes just to run their own infrastructure. In addition, if you're familiar with Kubernetes, you're familiar that you can monitor and you can scale your workload mainly based on CPU and memory. So you see how the system is behaving, so how much memory it's using, how many CPU is using, and based on that, you can even horizontally scale. This is not applicable here, because most of the computation is happening on GPU. At the same time, a small prompt can generate a very long answer, so you cannot do request-based scaling, because if you have 10 requests, the type of impact that they have on the system, it's very different. A very small request can have a very big impact on the infrastructure, because maybe generate a lot, and vice versa. So you need to use a different unit of measure. So the token is the unit of computation that is really representing let's say, that can be used to address or to estimate the impact of your system. So this kind of LLM engine, like vLLM, produces specific metrics to give you information about how much time it takes to produce the first token, how much time it takes to produce every other token, the overall number of tokens that produce, how many requests they are waiting, how many requests are running. So this is the way you can monitor a similar workload and understand if your system, let's say, the level of service is getting worse because maybe the latency is growing too much. Maybe the GPU is not still used entirely in terms of computation, but the latency is already going up because you are in the decode phase, you don't have enough memory, the computational power is there, but you cannot still scale. So GPU is a key aspect, of course, of this. So let's look at a bit more at GPU management. How many of you knows Kubernetes, have ever used Kubernetes? Or okay, a bit less than half of the room, okay. So Kubernetes design or architecture has a concept of control plane and different workers. So the control plane is where you describe what you want, like I want to deploy a container, a Docker container, and then Kubernetes automatically decide in which worker node, so in which of the node you have enough resources to schedule and to deploy. When you say GPU, well, the node, it's a virtualized or a physical, but it's your server, and then you deploy different pod. So maybe in your system you have two different nodes. One of them has GPU, and the other doesn't have. So Kubernetes has a concept of a device plugin, so you can essentially make Kubernetes aware that that node has a dedicated hardware, so has GPU, and sometimes you also have a GPU operator that simplifies the management. So overall, that means that when you create a traditional deployment on Kubernetes, usually you just specify like the image that you want to run, Nginx latest, and the requirement in terms of like, okay, I need one CPU, 10 GB of memory. When you want to deploy LLM, well, vLLM in this case, vLLM as a runtime, you have an image, you have a command that you run to say like, okay, start my model. But how can I express, like, I want a GPU? So I want that this deployment is placed in one worker node where, in a node of Kubernetes where a GPU is available. Thanks to the device plugin, it's very similar. So in the section of the spec where you were specifying, like, I want this one CPU, 2 GB of memory, I can say, like, nvidia.com/GPU2. That means, like, okay, I'm asking that this deployment requires 2 GPUs. So only schedule in a node where you can satisfy this requirement. Nice, it works. What is the limitation of this? It's a limitation that GPU nodes are expensive, so more likely in your cluster, only a very small subset of the nodes is going to have GPU. So you don't want to waste the computational power of that node to run additional stuff that does not require GPU. So I don't want that my microservice that maybe is just serving my web application is going to be scheduled in the same worker node, because at that point, I'm wasting resources. I might have different type of GPU. There are GPU given even that you cannot like go to your grocery store and take a GPU. So usually you need to order. It takes time to provision. It takes a lot of money even just to configure and set up. So it's very likely that in your cluster you're going to have a different type of GPU. Maybe some very big GPU, some smaller GPU. So you don't want that a very small model is taking a whole GPU, one of the biggest GPU, because it's a cost for you. At the same time, given that here we're discussing about physical hardware, so you cannot ask, I don't know, 20 GPU on the same node. If your model is big enough, and now we are looking at models that really requires 8, even more GPUs, you might not have enough GPU in the node where you are running, so you need to collect resources across different nodes. Or you have a GPU that is big enough to say, like, okay, my model is just taking half of them. Why should I take the whole GPU if I just need a portion of that? So I would like to fraction the GPU. So in Kubernetes, there is a concept of affinity where you can specify like 2 pod, so that is 2 containers might be scheduled next to each other because you say that they are, with affinity, they need to attract each pod, essentially, each other. There is a concept that is the opposite, that is stains, that is used to say like, if I use this label, essentially I'm repelling the workload. So I'm, let's say, making sure that nobody is using that, let's say, that node, except if you express the toleration. So express if you say like, this workload tolerate that specific trait. And this is the mechanism in which you should configure your cluster to say, like, my node, if it's a node that has a GPU, should repel, essentially, everything that is not explicitly configured to end in that node. And this is overall a pretty explicit way to configure, but it's pretty powerful because, for example, you can define different keys per the type of GPU. So you can say, like, the taint that you define in a node is like H100. It's a key. You can specify whatever you want. And at that point, you can specify the specific GPU in your deployment that you want to get assignment, or you can use node selector. In general, one of the key aspects about that is that if you are also, in addition to serving, that means like inference, purely inference, if you also do training, usually the training nodes has a very ad hoc and expensive way to configure the node, the network of the node, because usually for performance reason, you want to connect peer-to-peer his GPU with a very dedicated network that is pretty expensive. So you can use this approach even to completely isolate and say, like, a training node, it's very expensive. I just want to use that for training. I don't want that a simple deployment is going to land there because it's a waste of resources. I mentioned that sometimes you don't have enough GPU. So what can you do? Well, at that point, you cannot leverage the magic of Kubernetes anymore directly. So you need to create different deployment. So that means that you need to go multi-node. That means that you need to are going to run an instance or a deployment of vLLM per node, and you need to connect each other. Behind the scene, it uses Array. I don't know if you're familiar with the technology, but it's an implementation detail. Overall, one of the deployment is going to take the head role. That means that it's the entry point of this cluster of different deployment. And then you have different worker nodes that are connected each other just to, let's say, share the execution. It's critical at that point to configure tensor parallel and pipeline parallel. Tensor parallel split the tensor itself, and usually you need to configure in the size that you need to configure. It's based on the number of GPU that you have per node, while pipeline parallel that slice the model in terms of layers, usually it's based on the number of nodes. So as soon as you go multi-node, it's not really plug and play. You need to manually tune essentially what you want to obtain. And then at that point, given that you are going multi-node, the network across the two different nodes needed to be optimized. Optimized means RDMA, InfiniBand. There are technologies, so there are dedicated network interfaces that you install in the cluster that connect the physical cable to the other one. That is not the network interface that you use for the traditional pod-to-pod communication. So it became pretty custom. There are projects like KServe that give you let's say, an higher level abstraction API where you can deploy this model requires multi-node, and behind the scene KServe, it's a component that you can install in Kubernetes, is going to automate the creation of the different deployment. But still, if you open and you look at the inside, you will see that there are different deployments. Here, okay, GPU partitioning. This is I wanted to include that because it's a topic that sometimes you needed to use, because if you are buying, let's say, very big GPU, you probably wanted to use as much as you can. It's not transparent. It's not equivalent to the CPU. So I cannot say, like, I want 0.2 GPU. There is a concept in NVIDIA GPU in some of the models, the most expensive, essentially, that is called multi-instance GPU, that it physically define how many partition of the GPU, so how many slices of GPU you can create, usually 7. In the recent model, it's about 10. And then when you request that specific GPU, you needed to specify, instead of saying like generic nvidia.com/GPU1, like before, it's going to be MIG, the name of the GPU, the name of the slice that you want to use. Kubernetes is evolving overall as a, let's say, project with the concept of dynamic resource allocation that try to standardize that and make it a bit more, let's say, generic. So at the moment, what I described here, it's an NVIDIA-specific implementation that is available only in NVIDIA cards. There are other techniques about sharing the same GPU, like multi-process service and time slicing. They are not really designed for production. It's something that, let's say, I just mentioned it for a matter of, let's say, to be comprehensive, but I mean, it's not really something that I recommend. The last part of this presentation is going to touch something that is really like ongoing. I mean, it's not really like, if until now it was something that you already have in production, or I mean, many customers has in production, this one, it's like something that it's still, let's say, in the making. It's there, you can try. So what is the challenge? I did everything correctly. My deployment is there. I start to get traffic. I started to get more traffic, and at a certain point, I realized that, OK, a single instance is not enough. I'm getting latency going up. So, well, I still have maybe available GPU. Kubernetes does horizontal scaling, so why I cannot just do scale up? I create another instance. It's going to deploy a model. It's going to run it. And what is happening? Well, Kubernetes, by default, when there are multiple instances, is going to apply a round-robin mechanism for load balancing. So every request is going to go to one of the replica in a way that is completely like, let's say, uniform. What's the result? Well, the latency distribution can be very bad. And you can see that maybe one of the replica is going to have a very big queue time, so that is going to have a lot of requests that are remaining in the queue, not processed, and maybe another one that is in idle. Why this is happening? It's because in the nature of LLM generation. So a single prompt, a single request that is maybe small can generate a very long answer. So the time to process a request, it's not uniform. And you should not just, let's say, assign the request in a uniform way, because you should really look at what is the current workload. Maybe, let's say, bad luck, that replica got a very complex prompt to process, so that they're generating a lot of text. So that replica is still processing a lot, while another one maybe is in idle state. So probably to get better throughput, to let's say, improve the latency, at that point you needed to have a router, so a load balancer that is LLM aware. So before deciding where to assign the job, I really needed to understand, let's see how many jobs, how many requests are waiting in that replica. In addition to that, if your use case is like a chatbot or even RAG, you are essentially sending to the model a conversation. And every time you are sending the history of the conversation plus generate the next step. That means that if you think about the KV cache, the prompt is essentially always the same, plus an additional step every time, because it's the previous conversation, and now I have the new question that I added to the conversation. So if I'm smart enough, and the memory was like big enough, I can route the request to where the previous request has been processed, so that the information are still in the KV cache. Or even better, I might think about how can I share the KV cache across different replica, so that at that point I'm not let's say, pinning my end user with a specific replica, because regardless which replica is going to it, the KV cache is distributed. So we can think about a distributed KV cache, and you can even easily imagine that that has a very strict, strong requirement in terms of network. Because if you want to distribute this KV cache, you really need to be fast moving data from one replica to another. So we can do that, but it requires yet additional custom configuration. So when we mention prefill and decode, if you try to profile more or less what is happening, you will see something like that. So usually you have like a peak in prefill, and then you have a peak in decode. Because it's expected, like I first do the prefill, so I process the input and produce the first token, and then I do the decode, where I start to produce the others. You don't see an exact match like one prefill, one decode, one prefill, one decode, because again, maybe a very big prompt, so a lot of prefill work produce a single token. So they are not really, let's say, equivalent, but you can see this kind of, let's say, analogy. And that means that if in my use case, maybe I do RAG, I send you every time a lot of data, and maybe I expect a single answer, like, OK, can you classify all those data and tell me yes or no if you think that this is a valid input or not, whatever. So you're going to have a very intense prefill phase, because it's going to process all the data, and a very thin decode phase. So another scalability challenge is like, why I don't recognize that they have a different workload, and maybe I try to have a pool, so I needed to maybe scale just the number of replica that does the prefill, and not scale the number of replica that does the decode. So I might try to assign a specific role to one of my instance, and this is going just to process the input. One of the reasons about that is that I mentioned before a couple of metrics like time to first token and inter-token latency. So time to first token is literally the waiting time when I invoke ChatGPT before I get the first token. And this is, let's say, it has a very direct implication if it's a real-time use case about the experience that the user is getting. And then it's like the latency that the user is going to get for every other token. But for example, if it's a batch system, I don't really care about time to first token. I mean, it can take even 1 hour and collect all the information to try to use all the possible, let's say, resources that I have in my GPU so that I mean, if it's a real-time job or if a batch job, the type of experience is completely different. So, welcome to disaggregated serving. This is a picture about NVIDIA Dynamo. This project has been announced, it has been open sourced 1 month ago, roughly. It's a pretty complex, let's say, diagram. I'm not going to cover all the details, but there is an API server, of course. You still need to get the input, the request. Then there is a concept of smart router. So it's a routing component that is aware about the status of the cache, is aware about the status of the runtime. It's aware about the status of the runtime because there is a component that is dynamically taking the metrics from the runtime and sending this back to the router. So there is a very deep connection between these two components. Then I have that distributed KV cache. That means that I have a layer of abstraction between, before the KV cache was literally in the memory of the GPU. Now I want to abstract because it could be in the memory of the GPU, but could be even outside. And you can implement a hierarchical KV cache. So you can have a scenario where, of course, it's very similar to even CPU caching, to say like I have something that is in the CPU, and at a certain point I go to the central memory, at a certain point I go even on disk. Of course, you need to figure out let's say, at a certain point, you have a trade-off between fetching data from the cache compared to recompute the KV part, of course. And finally, there is a pool of pre-fill worker and a pool of decode worker that are going to do just the pre-fill phase or the decode phase. It's not the only project available on the internet. This other one is being created mainly by ByteDance and has been open sourced. It's reasonably similar, so you have, of course, an API on top. Then you have a smart router that is aware about the overall situation of the system. One difference is that here is not doing the pre-fill and the decode phase in 2 different instances. It's just having multiple replica, because I mentioned 3 different problems about scalability, because you can tackle each one of them independently. I can decide, I just introduce a router that is LLM aware, then I introduce a distributed KV cache, then I do so you really need to think about what are the requirements in terms of scalability, and based on that, even because some of them require additional hardware. So it's not for free. It's not like that's a plug and play. And finally, the distributed KV cache. Okay, I mentioned that I'm writing a book. It's published as early release at the moment on the website from O'Reilly. With that code, you can get access to the early release. It's roughly half of the book. Still not reviewed entirely, so I mean it's an early release. The final release is going to be out next year, roughly, Q1 next year. And yeah, feel free to have a look. Feel free to share comment or even ask a question about the book. Or if I still see people taking pictures. So 3, 2, 1. Okay. Too late? Okay. No, thank you. I mean, for question, I can stay on this slide if you want. Okay.
Thank you. Thank you very much, Daniele, for this wonderful and technical talk. Questions now? Who wants to be the first one?
It's lunchtime.
Yeah, it's lunchtime, and it's a deeply technical topic. So, yeah.
So thank you. It's more a curiosity rather than a real question. But like, how can someone that is already familiar with Kubernetes somehow implement some of these techniques in how easy it is, and is there any way to like, let's say, any tool or framework that helps you to implement this kind of optimization, or you're, at the moment at least, you need to go into the very detail of the configuration, YAML file, and whatsoever?
Well, of course, it's like the whole ecosystem is evolving. So if you compare how hard it was to configure even just a plain deployment without any requirement 1 year ago, now it's dramatically easier. So now in general, it's enough that you say like nvidia.com/GPU1. And if it's your cluster, you don't have, it's dedicated for you more or less, probably it's enough to start with. Everything else that I mentioned was about properly segregate the traffic, because when you go to production, you don't want a noisy neighborhood type of scenario. That is not entirely true in terms of the runtime, but it's more about the resource. I mean, I don't want to waste resources that are expensive. So that part about the tuning was more about how can I optimize my setup, while the last part about the disaggregated serving is something that is, it's still, I would say, in the making. At the moment, it's still pretty manual, the deployment. I expect that in the second half of the year, beginning of next year, things are going to mature in a point where you probably are going to just declare, like, I want to deploy this topology. I don't really care about how this topology, so I know that I want to have an LLM-aware router. This is going to configure the router for me. I know that I want to have a disaggregated cache, a KV cache, distributed KV cache. So that is my expectation.
Okay. Thank you.
Welcome.
We do have time for one more question.
So I understand that the code phase takes, I mean, I understand that the load on the code phase, but what makes the prefill phase variable in terms of load?
What do you mean?
You showed the graph where pre-code and prefill and the code phase are having different spikes on the cluster.
Yeah.
Yeah, I understand that the code could have a variable load, but what caused the prefill phase to have this?
Even for the prefill, because the prefill is directly related with the number of token of input that you are sending. So if you are sending a single progression, it's reasonably small. If you're sending maybe the whole, I mean, there are now models that accept, I think it was maybe a Gemini, 1 million token. Like Lord of the Ring is 500,000 token. So if I'm sending the whole Lord of the Ring in the request, this is going to produce a spike in the prefill phase, and maybe at the end, maybe a very small decode phase. So this is coming from the technical paper of Mooncake, that is another project that is developing this distributed prefill that is very well done. And I don't know exactly how they produce, or what was the workload that they used to produce that diagram.
Thank you.
Welcome.
We actually have time for one more. Yeah.
Hi, thanks a lot for the presentation. I was thinking about some techniques in the field of LLM inference, such as mixture of experts, or having hot swaps between LORA, LoRa models on the same foundation models. First of all, are they covered inside the book?
For the LoRa part, probably yes. For the mixed of expert, not that much, because from a platform perspective, I mean, the target audience for the book is really like someone that manage the infrastructure, like the Kubernetes cluster, that now need to manage a different type of workload. They need to understand how to scale, how to monitor, and how to overall understand what's going on. So it's not really model architecture specific. For mix of expert, the expectation is that now that they're also implementing expert parallelization, that this is going to more likely impact the way you tune that. While for LoRa, in particular, this project about AI bricks, it's using another project that is called the AI Gateway API Inference Extension. Well, the name is very bad, but whatever. That is LoRa-aware. So you can deploy, and vLLM support that. You can deploy the base model. You can deploy up to 4, I don't remember by heart, LoRa adapter on top. And at that point, the same instance is going to reply back using the base model or the LoRa base, the LoRa one, based on what you specify in the payload. And let's say this router component is aware about that, so it knows that when you're asking about model A or model B, maybe they are both on the same instance because in reality it's just a load adapter on top.
Okay, thanks a lot.
Welcome.
All right. Thank you very much. Again, a round of applause to Daniele.
Thank you.